Okay, so welcome to the seventh lecture. So today we'll be starting or we'll be discussing the chi-square distribution, and we'll be starting to understand how it can be used for various tests. Okay. So let me switch my camera. So today is Stat 313. It's lecture 7. So let's get started. So we have seen a chi-square distribution before, right? So let me remind you. So this is from the first lecture that we did. Uh, we had, so this is from my lecture 1. If you go to the 7th page there, so here we started the chi-square distribution, right? So chi-square distribution with certain degrees of freedom R is it has a probability density function given by this one. Okay. Also, if we have, say, independent random variables and each of those following chi-square with certain degrees of freedom, then there's sum that follows a chi-square with the sum of the degrees of freedom. Okay, so that is another result. We sort of mentioned it there. Now, based on this, we are now ready to consider some tests for chi-square. So what we'll write is the following. Let x1 is a binomial is following a binomial distribution with parameter n and p1. Consider our random variable, say y, which is given by x1 minus n times p1. It's its expected value, so its expected value is n times p1 for the binomial, and its variance is n p1 1 minus p1. As we all know, these are the expected value and variance for the binomial distribution. So suppose we consider a new random variable y, which is given by x. So we write x1 minus np1 over the variance, which is np1 1 minus p1. Okay. Of course, by the central limit theorem, so as n goes to infinity, this y is approximately standard normal by the central limit theorem. Okay. Now we have seen that the square of a standard normal is a chi-square distribution. So remember that if z is the standard normal distribution, so that means it's normal with mean 0, variance 1, then z squared is chi-squared with 1 degrees of freedom. And therefore, what we know here is y squared, since y is approximately normal for n goes to infinity or n large, so y squared would approximately be chi-squared with 1 degrees of freedom. Okay, that's our first observation. So if x1 is a binomial distribution and we constructed y in this way, then y squared is chi-squared. Okay. Next, suppose I define another random variable x2, which is not independent, but it's n minus x1. Okay. So that means basically whatever the value of n is, and n is from here, so I subtracted x1 from here. And define let p2 be 1 minus p1. Okay. Now let us consider, so let's call this one by a name. So let's call this y squared. You'll pretty soon see y, but we'll call this as q1. This one will be seeing y, this one. because, oh, well, it simply says that it's following 1 degrees of freedom. Now, Q1, okay, so after this two redefinitions or two new definitions, X2 and P2, let's define then Q1, which is given by X1 squared minus NP1 squared. Remember, it's Y squared, and this is Y, so I'll just square it. So it's going to be NP1, 1 minus P1, right? Now, I can write this in the following way. I can write this, and I'll leave it up to you to check it. So it can be written as X1 minus NP1 squared over NP1 plus X1 minus NP1 squared over N1 minus P1. It's very easy to check. What you do, you simply just add these two. And when you add these two, you'll see that you'll recover this one. Okay. Now note that I'll do a little calculation here. So note that if I want to compute, say, X2 minus, here is an aside. What is that? So suppose I want to compute X2 minus NP2 squared. Suppose for some reason I want to compute it. What is X2? X2 is N minus X1. And what is P2? 1 minus P1. So let's use it here. So it's N minus X1 minus N, 1 minus P1 squared, right? So if I just FOIL it out, so it's N minus N and plus N cancels. So I have minus X1 plus P1 squared, which is same as X1 minus P1 squared, right? In other words, X2 minus, sorry, there is an N here. I forgot to write that in. So in other words, X2 minus NP2 squared is same as X1 minus NP1 squared, provided we defined X2 as N minus X1 and P2 as 1 minus P1. Okay. Let's plug it back here. So what we'll do is there are two X1 minus NP1. For the second one, we'll be replacing that by what we obtained. Okay. So what we write here is we write X1 minus NP1 squared over NP1. Basically, we copied this thing. Okay. For this one, we'll write X1 minus NP1. We'll replace that by X2 minus NP2 squared. Okay. So this is X2 minus NP2 squared. Now also, we have 1 minus P1, that is P2, right? So this is P2. So Q1 can be written as this one. So hence we see that, Q1 can be written. So if there are sort of two variables, two random variables, X1 and X2, where X1 is just following binomial distribution and X2 is defined this way, then Q1 can be written this way. Okay, so let's write it down. So what we just obtained is hence Q1 can be written as X1 minus NP1 squared over NP1 plus X2 minus NP2 squared over NP2. Okay. Now, please note the properties of X1 and X2. So remember that X1 equals to N minus X2. And P1 equals to 1 minus P2. In other words, if I just add X1 and X2, it's always N. And also, if I add P1 and P2, it's 1. For those who took course before, if you're familiar with the multinomial distribution, with parameters here. So basically, it's same as binomial because we have just two parameters. So I mean, if you're familiar with the multinomial distribution, say if we have now, say x1, x2, xk minus 1. So let me just write this way, multinomial distribution on x1, x2, xk minus 1 with parameter p1, p2, pk minus 1, and define, suppose we define x sub k as n minus all the previous sums, k minus 1, and p sub k is 1 minus all the sums of the p's, p of k minus 1. If we did that, so basically what I'm writing here for, I mean, so after we obtain this Q1 corresponding to this one, we want to generalize it. So it's a generalization. Okay. Please note that here, I'll come back to this one, but before doing that, please note that here this x1 and x2 are, I mean, this x2 is constructed out of x1. Right, so it's not just two independent random variables. So x2, once we specify x1, we know x2. Okay. Suppose the value of n is 20, the value of x1 is 19, then x2 got to be 1. Okay, their sum must be 20. So what is the generalization? So suppose now, and we have seen that in that case, my chi-square can be written as this way. Now the generalization is, suppose now we have, instead of, I mean, here we had just one and we constructed the second out of this based on the value of n. The concept is, suppose we have k minus 1 distributions with certain parameters, and we define the last one by xk equals to n minus the previous one. If you can think that previously we have just done a special case of it for k equals to 2. Right, so we have x1 and x2 and we define this way. So last time we have done a special case, but here we are defining it for initial k minus 1 random variables. Now if we did that, it's a multinomial distribution with parameters with sorry, I forgot to write the other one, with parameters n and this one, parameters n and P1, P2. So N is the total number of trials, and P1, P2, etc. Pk minus 1 is the probability of getting x1, x2, xk minus 1. And note that I'm defining xk in such a way that now there is, when I add x1 through xk, I'm always getting this number n. Okay, so it's sort of an artificial random variable. Okay. Define, now motivated by the previous one, let's define q sub k minus 1 equals to the summation of all such things, right? So I'll define this by summation I from 1 to k xi minus npi squared over npi. Just look at the previous expression that we have. It's the summation of two terms, xi minus npi over npi, and we are writing it for the k terms. So let's define this way. It can be shown, will not show it. It can be shown that as n is large, this qk minus 1, it approximately follows a chi-square distribution with degrees of freedom k minus 1. Okay. All right. So, by the way, and also we have already seen that Q1 follows chi-squared of 1. Okay. So that's, I mean, we already know that this notation Q, where it's going. So whenever I have a random variable Q of k minus 1, I'm saying that that's approximately following chi-squared k minus 1. How do we construct this? Well, I have a bunch of sample values. Only remember that by sample values, I mean that we are given with k minus 1, and the last one is always constructed this way. So you don't construct all the random variables, you just use k minus 1, and the kth one is constructed out of the previous random variables. Okay, so that's just um, little subtlety. Okay, now, okay, so now at this point, let me show you, and this is a link that I'll be posting on Brightspace, so we can check it there. But let me share my screen and show you how to compute the critical values of chi-square distribution. We'll be talking about this one pretty soon. Okay, and that time I'll again show you how to do it. But here the idea is go to this website, and again you don't have to go here. I mean, there are many other calculators online. Please feel free to use whatever you want to use. What you do is in the distribution section, so you see this distribution. So by default in this page, it's set up as normal. So you change it to chi-squared. Now, for the tails, you'll be writing the right tail. For the significance level alpha, you'll say 5% significance level, and degrees of freedom, whatever you want to put, say 4 or 5, say. Okay, and rounding, you don't have to touch it. It's whatever rounding you want to. Now, if you calculate this, you'll see a picture. So this picture shows you this is a chi-square distribution with degrees of freedom 5, and the critical value is 11.0705. Which one is this one? So this is this values. This number right here. So this value is 11.0705. Okay. So this way you can compute the critical value, and you'll see why, because in the next example, I'll be using the critical value. So this is a nice way of computing the critical value, meaning that this value for a chi-square distribution. Okay. Okay. All right. So now with this, let's see. So here is an example. And this is called let me just talk about this a little bit, because this is very important, and I plan to do some exercise based on this goodness of fit test. Okay, so testing for goodness of fit. Okay. And typically it's done by chi-squared. Okay, so here the problem is we want to test, once again, test of hypothesis. We want to test whether a population distribution is of a specified kind. Okay. So, and it'll be more clear when I do the like the example, but just bear with me for a bit. So suppose that the population has k classes with pi being the unknown proportion of the ith class. So that means I is 1, 2, up to k. Now the null hypothesis H0 is P1 is say P1 0, which is known. So I'm trying to test what is, so there are basically k classes of the population. So let's have this classes. So maybe there's a first class, second class, third class, so on. We have the k classes of the population. Okay, so we sort of maybe divide this population in this k buckets. Okay. What is this? I mean, this. Sorry, PI. Okay. So what are we saying? So we are saying that for the class 1, the proportion is p sub 1. For class 2, the proportion is p sub 2. Class 3, proportion is p sub 3. Class k, proportion is p sub k. We don't know. So those are the unknown proportions. Okay. We are trying to estimate it. So, and we are trying to estimate it is in the following way. So P1 is unknown, but suppose we know a number. So suppose our conjecture is say P1 is 1 over 16. So that is a known number. That's what I meant by that. P2, suppose my second conjecture is P2 is also 1 over 16. And so on. Pk is Pk0, which is known. Okay. And known, how do you know it? It's well, so we are trying to we'll see how it works. So basically, this can be computed from the sample, and then we can test the hypothesis. How do you know it? So it's considered like known. We'll see how to do it when we do an example. Okay. Okay. So I think I'm really not comfortable with this word known. So let's write this as specified. Yeah, that's a much better word. Specified. Here it's specified. All these are specified. Yeah. Okay. How? We'll see. By the way, I must mention another thing. So since this K sort of classes are constituting the whole population, so let me just write one more. P of k minus 1 is P of k minus 1, 0, which is also specified. Please note that when I add, I mean, these specified numbers, they should add up to 1 because they are the proportions. In other words, so P of k 0 is really where 1 minus P of 1, 0. I don't know how I wrote it. Let me just put a parenthesis here. There are many ways of writing it. P2, 0 minus all the way up to P of k minus 1, 0. So the goal is to test this hypothesis. And we'll be testing this against an alternative. So we desire to test H0 against all alternatives. Okay. How do you do it? The procedure, the standard procedure is compute a test statistic. Statistic is computed as under H0. Let's compute summation of the there are two different ways of writing it. So I'm just debating which one I should write. So let me write this in the following way, and then I'll explain. So let me just write xi minus npi0 squared over npi0, where I is running from 1 to k, which is similar, which is very similar to what we wrote before. And you know that this is basically a chi-square distribution with k minus 1 degrees of freedom. Okay, so in this case, this will be chi-square as long as I'm defining what this, which I never defined so far. So I have to define this x1. So let me just do it. Where what is xi? So where xi is when this random experiment is repeated n independent types, xi represent the number of times the outcome is an element from this population class k. Okay, so it's a number of elements observed from population class I, or let's write here k. So it's k. Okay. Okay. So basically, this is the observed value of the population. And by the way, also please note that if I specify the entire population, which is suppose I specify this to be n. So if the population size is n, if the population size which I actually assumed right here is n, then this quantity q of k minus 1, which is equal to I from 1 to k xi, I wrote it before, n of pi0 over n of pi0, it follows a chi-square distribution with k minus 1 degrees of freedom. By the way, then this is what I was about to write and then forgot. So then x of k, I have k buckets of population. So we have k classes. So class 1, 2, k. So the total number is n. That's the picture to keep in mind. So we have k classes and total n. So that means x of k is really it's n minus x1 plus x2 all the way up to x of k minus 1. Remember that the last one, this is the classic setup of the chi-square. The last one is dependent on all the first one. The first k minus 1 are independent, but the last one, it's basically n minus that thing. And that's why it has k minus 1 degrees of freedom. Again, we didn't formally prove it, but it can be done. Okay, so that is the quantity we're talking about. And now this follows a chi-square distribution. So we can do whatever test we want to do it. So the decision rule would be, well, higher the deviation. Remember, this is the observed ones, right? And this is the expected one. And you will see this in much better terms when I write the example. Higher the deviation between the observed and expected values, the greater is chi-squared. So of course, if these numbers are bigger, so if the difference is bigger, so this chi-squared will be bigger. And therefore, we will reject H0 at level alpha if the chi-squared observed, which is the Q of k minus 1 value, that is what the observed chi-squared, it's bigger than a chi-squared of some alpha with k minus 1. And accept or retain H0 otherwise. That's the goal. Okay. All right. So by the way, so this notation, I think it's clear by now, but let me just mention. So here, this chi-squared alpha k minus 1, this really means the upper alpha point of chi-square distribution. I showed you a picture some time back, and I'll show it again sometime after some time. For example, I mean, the chi-square pictures, they typically look like when you have, say, it's something like this one. This is 0. And this is a value of chi-squared alpha k minus 1, provided this area here is alpha. So what we are saying here is as simple as that. Like if we are observing something, a chi-square value somewhere here, we reject the null hypothesis. We say that the observed values are not in agreement of whatever proportions we are specifying. Okay. Now this is a little theoretical, so let me just quickly do an example. And this example will make it very, very easy. And it's actually a very easy concept. Okay. So first example. Suppose we throw out dry. And the null hypothesis is, so basically we have outcome are 1, 2, 3, 4, 5, and 6, right? So the null hypothesis is basically, I'm saying that P of 1 is 1/6. So null hypothesis, it's a fair die. So P of 2 is 1/6, P of 3 is 1/6, P of 4 is 1/6, P of 5 is 1/6, but note that this is sufficient because P of 6, which is really 1 minus P1 minus P2 minus P3 minus P4 minus P5, that got to be 1/6 if the first 5 are specified. Okay. So this is the last information is redundant. Like if you somehow get all these numbers to be 1/6, the P6 got to be 1/6. Okay, this is what I meant by the word specified before. So remember, so as I mentioned, so this will be my P10 is 1/6. So this is really the P10 in notation. This is really P20. This is really P30, P40, P50, and this is, of course, P60. Once again, if the first five are classified, or first five are given, then you can compute the sixth. Okay. So H0, which is the null hypothesis, that the die is fair. Okay. And H1 is the die is unfair, meaning that maybe two of these numbers, it's maybe we don't care, like it can be various combinations. Maybe P1 is slightly more than all the rest and so on. Maybe all the numbers are different. It can be whatever. Okay, so we are testing this against all possible combinations. Okay, now, so here is the solution. So what do you have to do? We know that this is a problem for which we need to throw the die sometime, because we have to draw a sample. How do you draw a sample? So to make the test, we throw the die 60 times. That we can always do. Now, if we did that, again, I'm referring back to the previous one. So here, these numbers, remember that this is something we wrote before. Here, x1 would be the number of times I observe 1 if I throw the die 60 times. X2 would be number of times I observe 2 if I throw the die 60 times, and so on. X6 will be number of times I observe 6 if I throw a die 60 times. What is n? That is 60. What are these numbers? Pi0, I already classified those. All these numbers are 1/6. Okay, so the observed value, this is what I mean by the observed value, and this is the expected value. So what is the expected value for getting, say, number 1? If it's a fair die, and if you throw it 60 times, so 60 times 1/6, that means 10 times we are expecting 1, and that's why that is what we wrote as expected value, right? So let's do that. So we have, let's write, say, xi. It denotes the frequency of getting the value I, where I is 1, 2, 3, 4, 5, 6. In other words, x2 is number of times you get 2 out of n equals to 60 trials. Okay. Okay. Now, suppose we see the following numbers. Let us consider a sample space where x1 equals to 13, x2 equals to 19, x3 equals 11, x4, number of times we see 4 is 8, x5, number of times we see 5 is 5, and x6, number of times we see 6. So if you see that, then the summation of xi's, you can check, I from 1 to 6 is 60. If you add all these numbers, it's 60. Okay. So let's compute the test statistic. We're done. So test statistic, which is given by Q5 in our case. What is that? Well, it's first take a number 13 minus 60 times 1/6, that is 10 squared over 10, plus 19 minus 60 times 1/6 squared over 10, plus 11 minus 10 squared over 10, plus 8 minus 10 squared over 10, plus 5 minus 10 squared over 10, and finally 4 minus 10 squared over 10. Okay, so if you compute this, this is 15.6. So we found the value of the test statistic. Now we have to compare this. We have to accept or reject this, right? So we have 5 degrees of freedom. So suppose we are saying that we are trying to see what is the confidence interval. So let's take the significance level 5%. Okay. So let's take significance level equals 5%. So that means alpha is 0.05. What is the degrees of freedom? So degrees of freedom was 5 for this problem. Remember? So we wrote Q5. If there are 6, the last one is dependent on the first 5. So there are degrees. So there are really free variables are 5, right? So that means what is chi-squared 0.055? So let's see. So that is our test value, right? So so here is the thing. So I'm trying to see what is this area. So if alpha equals to 0.05, what is the corresponding number for degrees of freedom 5? Now let me just share the screen again. And here, what we have to do, we have to see chi-squared right side, check right, significance 0.05, degrees of freedom 5. It's already there. Calculate. So I got it 11 points. So the value is 11.07.0705. Okay, so that's the value you obtain right here. And if you want to see it where it is in the plot, it's right here. All right. So now, therefore, let me stop sharing. So I wrote this number. So this value is 11.0705, this chi-square value. Now, where is our test statistic value? Our test statistic value is 15.6. Okay. So 15.6 is somewhere here, which is Q5, the observed value. Okay. So since chi-squared observed, which is really Q5, which is really 15.6, is bigger than chi-squared 0.05 with 5, which is really 11.0705. Therefore, we reject H0 with 5% significance level. So what is the conclusion? The conclusion is the die that we considered, it is not fair. So the die is unfair. That means there is something, some bias somewhere. Okay. So this is how the goodness of fit, this procedure is implemented for testing hypothesis. Okay, it has another. It's also has another name. It's called so this chi-squared. It's called a Pearsonian chi-squared. Okay. Because it was discovered by, devised by Carl Pearson. And for goodness of fit tests. What is the goodness of fit test? That is what we have just shown, one of the examples. We'll do some more. Okay, so let's solve another problem. So suppose we have this one. So let's see. Okay. Next example. It goes like this. A survey of 320 families with 5 kids, 5 children, each revealed the following distribution. What is the distribution? So number of boys, number of girls, and number of families. Okay. For 14 families, there are 5 boys and no girl. Okay. For 56 families, there is 1 girl and 4 boys. Remember that we are considering 5 children each family. For 110 families, 2 girls and 3 boys. For 88 families, 3 girls, 2 boys. For 40 families, 4 girls, 1 boy. And for 12 families, 5 girls, no boys. Okay. That's a little table that we are getting. So it's from the survey. Okay, so that's the data that is provided. Is this results? Now here is something you're trying to check. Is the result consistent with the hypothesis that male and female births, biological births, are equally probable? Okay. So use 5% significance level. Okay. All right. So now it's a real science question. Like, I mean, this is how you can test something in practice. So suppose you get something from the survey, data like this one, and you're trying to do some meaningful testing. So here's the solution. So here the null hypothesis age 0 is male and female births are equally probable. By the way, so there are total 320 families, meaning that when you add all this, so if you add this, so here is a, if you write the total, it's 320. All right. So that means the probability of a male birth is 1/2 and probability of a female birth equals to 1/2. Probability of female birth is also 1/2 under the null hypothesis. What is the alternative hypothesis? That they are not equally probable. That means male and female births are not equal probable. We are not trying to claim which one is more for the alternative. We are just saying that they are not equal probable. Okay. Okay. So let's consider X. So what is the X? So X denote the number of boys in a family of 5 kids. Okay. Now then, so if X is the number of boys, so now forget about this survey. So suppose we are just considering the null hypothesis, where male birth and female birth are equally probable, and X is the number of boys in a family of 5 children. So X definitely follows then under H0. X follows a binomial distribution. So basically, I have 5 children, so 5, and with equal probability 1/2, right? So what is P of X equals to, say, little x? So that is 5 choose X, 1/2 to the X, 1/2, that is 1 minus 1/2 to the 5 minus X, which is 5 choose X, 1/2 to the 5 for X 0, 1, 2, 3, 4, and 5. So these are the probabilities of the binomial under the null hypothesis. Okay. Therefore, what is the expected frequency or expected number of say 5 boys in a family of 320? Okay. So basically, I have under the null hypothesis, I have all these probabilities. So therefore, I can simply write, so the expected frequency of the value of X, where X is 0, 1, 2, 3, 4, 5, for 320, that is my N, families is, basically I have to multiply 320 times 5 choose X, 1 over 2 to the 5. Okay. For X equals to 0, 1, 2, 3, 4, and 5. For example, how many families we are expecting out of those 320? How many we are expecting with 0 boys? So it's basically 320 times 1 over 2 to the 5. Okay. These are the so-called, if I want to follow the notation, so the notation that I showed before is this one. So if I want to follow the same notation, so this is really this part. So what we computed here is N of P of X0. Okay. Therefore, the test statistic under H0 is given by, we have how many? So we have X values are between 0 and 5. What do you do? So we have observed value. So those are the values that we denoted as these numbers. Okay. So let's write this observed values as a X. So here X is observed values. I have various values of X. So let's see. I think a right notation would be, say, X, because I have no, this X is the number of families. So it's let's write this as this is, say, Xi. So this is X1, sorry, X0 equals to this one, X1 equals to this one, X2 equals to this one, X3 is 2. Sorry about that. No, it's not right. So X is the number. X is the number of boys in a family of 5 children. So really, it signifies the family number. So it's X0 is this one, X1 is this one, x2 is this one, x3 is this one, x4 is this one, and x5 is this one. Okay. So those xi, so this xi, where I from 0, 1, 2, 3, 4, and 5, so they are observed frequencies of families with I boys. Okay. Now let's use it here. So now I have a notation for this one. So xi minus, we have already computed the expected values, which are 320, 5 choose x, 1 over 2 to the 5. That's the expected values. And here it will be dividing by, squared and divided by the expected values, which are 320, 5 choose x, 1 over 2 to the 5. Compute that. So the thing is, it looks not that easy to compute, but if you really compute this, so let's basically here we have the observed value minus expected value. So if you compute the expected frequencies, meaning this term, for various values of x, 0, 1, 2, 3, 4, 5. The first number would be, if x is 0, so this is basically, it's easy, 320 over 1 over 2 to the 5, which is 1 over 32. And therefore, 1 over 32 times 32 is 10. Then the next one would be similarly 50. Third one is, I'm basically plugging in the values, x values, okay? So 50, then it's 100, then it's 100, then it's again 50, then it's 10. Those are the expected frequencies, meaning this quantity here. And this xi's, the observed, it is given to be 14. So I'm just copying this one. So 14, 56, 110, 56, 110, 88, 40, and 12. So now from this little table, you can compute this number, right? So you have all these things. So these are the expected frequencies for various values of x. Okay. Now, I'm just not comfortable with this notation I here because I have x here. So let me just change it to x sub little x. Okay, if that makes sense. So this is the observed value for x equals to 0, observed value for x equals to 1, and so on. Yeah, so that is, I think, much better notation. So let's write here x. Okay. All right. So now, if you compute this quantity, it's just a pure calculation, and you can use some coding or whatever. So you'll get it 7.16. Now we are trying to test this hypothesis. What is so this is the observed value, right? So this is how many what is the degrees of freedom? So here the degrees of freedom. So there are 6 variables. So degrees of freedom is 5, right? So 6 means we have to write 5. So what we get is chi-squared observed, which is Q5, is 7.16. Now the problem is asking you to test the hypothesis with 5% significance level, right? So that means I have to compute chi-squared 0.05 and degrees of freedom is 5. What is that? So let's again go to the calculator. So we have to specify That's 0.05 and 5. Oh, we have already done it. So this number, we have seen it to be 11.07. 11.0705. Okay. Hence, what we have, so we have chi-squared 0.055. So this area is 0.05 and its value is 11.0705. What your chi-square value is, it's 7.16. That's the observed one, which is much less than the whatever the significance level is given. So chi-squared observed is less than chi-squared 0.05, 5. Hence, we accept. So we do not reject the null hypothesis in this case. We accept it because it's not the difference is not big. So we accept H0 at 5% level of significance. And conclude that male and female births may be regarded as equally probable. Okay. All right, so this is a classic example when this chi-square distribution is used for checking the goodness of fit. There are many other things chi-square distribution is used for, but in this course, we'll be specifically focusing on the goodness of fit estimators. Okay, so meaning that how good this fits the distributions, and hence I'll not focus on the other parts of this section. So I'll just keep on doing the goodness of fit. So let's do one more example. So this goes like this. A point is to be selected from the unit interval, say x between 0 and 1, by a random process. So we'll be picking up a point. So we'll be picking up a point from the unit interval using a random process. Okay. Now, suppose we have we are dividing this entire interval in 4 parts. So we have a sub 1, a sub 2, a sub 3, and a sub 4. So we have 0 through 1. Out of this, we are dividing between 0 and 1/4, then 1/2, then 3/4. We call the first part to be a sub 1. We call the second part to be a sub 2, third part a sub 3, and final part to be a sub 4. Okay. So in other words, what we're doing here is a1 is x such that 0 less than x less than 1/4. A2 is x such that 0 less than x less than 1/4 less than x less than half. A3 is half less than x less than 3/4, and A4 is x 3/4 less than x less than 1. That's how we are choosing the points between. Since now the way I wrote it, it looks like the these 3 points are not included. Let's make it include also. So let's write A1 includes this one, A2 includes this one, 3/1/2, and A3 includes 3/4. The last one does not include the last one. Okay. Okay. So now let. So we are basically picking up points in these intervals, right? So let the probabilities pi, I from 1, 2, 3, and 4, assigned to these sets under the hypothesis be determined by the PDF fx equals 2x when 0 less than x less than 1, 0 otherwise. How do you pick these sets? Well, it's from this PDF. So the probability of choosing something from A1, basically it will be integration of this 2x between 0 and 1/4 and so on. Okay. So under the null hypothesis, okay. So under the hypothesis H0. So my hypothesis is that the probability of choosing A1 is H0, which is given by this 2x. So H0 includes this probability density function. So that means my P of 1, that is probability of choosing this first one under the null hypothesis, is given by 0 to 1/4 2x dx. If you compute it, 1/16. P of 2, 0. So that means probability of choose. So this is, let me just write in words. This is the probability of choosing a point in A1 okay, under the given PDF. So suppose for some reason we have reasons to believe that the PDF is given by 2x. And in that case, probability of choosing a point from the first interval is 1/16. Probability of choosing a point from A2 would be 1/4 to 3/4 2x dx, which is 3/16. You can check. P30 would be 3/4. Sorry, it's 1/2. It's not 3/4. It's 1/2 to 3/4 2x dx, which is 5/16. Now P40, you can either compute the integration, or you can simply write 1 minus P10 plus P20 plus P30, which is equal to 7/16. Now, once again, what are the zeros? So my null hypothesis is that this is the PDF. So since we are computing this using the null hypothesis, I'm writing 0. So those are the specified values. Okay. We want to check these specified values. Okay. So that is the goal. Now we'll be checking. Now suppose so this is I mean, if this is true, then probably we verify the null hypothesis. Now what is the output on the basis of which we are trying to conclude something? So suppose, just a second. Okay, so suppose that we are observing 80. So we repeat an experiment that picks up a point between 0 and 1/4 0 and 1 for say n equals to 80 times, independent times. Okay. All right, so therefore, what is my expected? So expected under age 0 values of, say, if I write n of p1 0, so that is 80 times 1 over 60, 1 over 16, which is 5. N of p2 0, which is 80 times 3 over 16, which is 15. N of p3 0, which is 80 times 5 over 16, which is 25. And n of p4 0, which is 80 times, finally, 7 over 16, which is 35. So these are the expected values, right? Suppose the observed values of this experiment that we mentioned. So when we consider this experiment, suppose we observe frequencies in A1 to be equals to 6, in A2. Remember, what are A1, A2, A3, A4? So the first one is A1, this is A2, this is A3, this is A4. Shorthand. So in A2, suppose the observed is 18. In A3, the observed is 20. And in A4, the observed is 36. So now we have the expected frequencies and observed frequencies. Okay. Now, there are 4 intervals, so I can construct a chi-squared of 3 degrees of freedom. So test statistic is given by well, in the notation of what I wrote before. So this is really, so this is x1, this is x2, this is x3, and this is x4, right? So what is the Q3, the way we construct the test statistic? So this is basically I from 1 to 4. Remember, it's 3, but we are adding all the 4. So it's basically xi minus npi0, that's expected squared, over npi0. This is the formula I'm again and again using. Okay. So it's essentially, this is 6 minus 5 squared over 5 plus 18 minus 15 squared over 15 plus 20 minus 25 squared over 25 plus 36 minus 35 squared over 35, which if you compute, it's 1.83. So that is the value of the test statistic. Now, what do you want to do with that? So from the value of this test statistic, so now let's see. We are trying to, suppose we are trying to test the hypothesis with, let's see. Let us consider alpha level to be, say, 2.5%. So now then what is, so this is basically 0.025, right? So what is, so we already seen the observed one. So this is really what we found here is the chi-squared observed. So what is the chi-squared with the 3 degrees of freedom? So let's compute this from the table. So I go back to this chi-square. I have significance level 0.025, and my degrees of freedom here is 3. So if I now calculate this, I get 9.3484. Okay. So I'm just trying to see if the answer is correct. Yes, it is. So it's 9.3484. Okay. And hence, what we found is following. So therefore, the observed chi-square, which is right here, 1.83, is much less than the chi-squared, sorry, this chi-squared with the significance levels, this one, which is 9.3484. That means we cannot really say that we cannot fail the hypothesis H0, or we cannot fail the null hypothesis. So we fail to reject. Hence, we fail to reject H0 at level 0.0250. Okay. So that means what is the conclusion? The conclusion is actually if you have an observation, so suppose you randomly pick up points from this interval 0 to 1, and you see this bunch of numbers. So maybe you listed how many times it appears in A1, how many times it appears in A2, how many times it appears in A3, and how many times it appears in A4. And you list those numbers. And if you get, say, 6, 18, 20, and 36, then what is your conclusion? Actually, you have you have a conclusion that it comes from PDF, which is fx equals to 2x. Okay, so you see how powerful these tests are. So actually, you're now you have with the significance level 0.025, you can say that. Okay. All right. So this is one very important aspect of using chi-square distribution for those who are interested. So chi-square can be implemented in many other cases. For instance, chi-square is used to check if two distributions are independent or not. Chi-square can be used to see if a sample is coming from a particular proportions. So many other things like that. So you can read the book, but for as far as this course is concerned, so we'll be just focusing on the goodness of it, meaning that how well can we say that if we have a specified set of parameters, how can we say that our hypothesis is actually saying that yes, those specified set of parameters are true. What is the alternative hypothesis? That those specified set of parameter is not true. Okay. So that is pretty much it. Next time, so we are done with this chapter 4 from the textbook. Next time we'll be starting chapter 5. Okay. So thank you, and let me stop recording.